Chapter 6, Routing Protocols. The foundation topics that the book talks about: basic routing process, source of routing information, routing protocol characteristics, routing protocol examples, address translations, multicast. These are things that we're going to need to use to function in our routers. So routing protocols, we're going to make decisions based on source destination, how we're going to send that. Another thing, how do we route protocols between different routing protocols? When using multiple routing protocols, how do we reach our destination? How do we pick that route? Well, we're going to see about some stuff like that. Like an example, we're going to learn about administrative distances that's going to take the place of this. Similar to like when we looked at the costs in STP, when you have Ethernet is, I think it was 19. Well, as an example, we're going to learn about the difference between routing protocols. We're going to have two categories. We're going to have distant vector, link state protocols. They differ from each other. We're going to talk about network translation. So this is where we have a single IP, and we're going to communicate across. We're also going to talk about a little bit about multicast, traffic. So routing traffic, we're essentially we're flowing traffic between two different networks or multiple networks, trying to figure out the best way to send that data there. We're going to, the book's going to introduce us to a couple of different routing approaches. We'll see how these all go. So here's a basic routing topology. So the book is showing us an example here. We have two routers. Between them, we have PCs on each end. We have a switch. We have MAC addresses. We have Ethernet. We have a serial connection. That's what the yellow lightning bolt is for. So this shows us an example, basic idea. PC1 cannot send a packet to server 1 on the remote network unless there's an intermediate device to forward these packets. Well, that's the job of a router, right? Send it from one network to another network. That's what routers do. That makes sense. So here, talking about step 1. We're saying, hey, the PC is going to do an ARP request because it needs to know. Because remember, when we're talking about sending a packet, what are some of the components of a packet? We have to have source, destination, IP, MAC address. We need destination IP, destination MAC address. We need these pieces of information. So we're going to do an ARP broadcast. So we're going to say, hey, and the router's going to respond. The data is going to be sent across. Here's step 2. Now, the router looks at the IP. So now it doesn't know the MAC address and the destination. So in our frame, so we have, in our route entry, here's what it shows. Then step 3, here we're getting the routers to doing an ARP cache too. So it's doing an ARP request, doing the reply. So now we have that information together. So now we can send that across. Source of routing information. Routers can learn about distance networks through directly connected routes. They learn through physical connections. We have static routes where we manually configure them by the administrator. So we also have a particular one. It's called the default static route. So if we don't know how to find it, send it to this person, let him find it. We have dynamic routing protocols. We can do a mixture of all these. We can do a mixture of static and dynamic routing protocols. There's different reasons that we're going to do this. Here in this diagram, we're going to see connected routes. So router 1's table knows 2 network routes. Router 2 knows 2. So now we have the problem is we have 3 networks here, right? So we can't go from PC1 all the way out to the internet because we don't know how to get there. Not yet. So what we're doing is we're adding a static route saying, okay, Anything that doesn't match the top two choices, send all the other choices to this interface and let him make that decision. And the same thing down here. You're going to see we're going to make a couple decisions too. So router 2 has 2 additional entries in there. He's saying, hey, send whatever to the internet out through its one interface, anything to the 192.168 network, send it out to this interface. So this way, what the 00 means is, hey, if it doesn't match this list, send it this way. It's a matching pattern. So what we're looking to do is match something. And remember, we're always using, most of the time our networks are going to be with a 0 at the end or an even number. So if we took like an example, if we took a Class C address and made it smaller, we could have even numbers there, but typically we're going to have zeros across. So dynamic routing protocols, the advantage of that is these routers automatically advertise their directly connected networks to each other. So they can build this table or static routes to their neighbors. So neighbor routes processing information determines the best path to any remote network. So based on these different calculations, they would come up with the costs. Like an example, if we're using Google Maps, whatever mapping program you're using, and sometimes they may give you alternate routes to choose from, and then you're going to pick that route that you feel like is the best choice. Well, we can do the same thing. We assign metrics or values to each route. So directly connected have a value, static has a value, and the different routing protocols have their values. Now, here's some of the examples of routing protocols versus routing protocols. So routing protocols like RIP, OSPF, EIGRP, they're internal. So what that means is, let's say we have 5 different networks. We use those routing protocols to route our traffic. And BGP would be essentially ISP provider level, like your Comcast, your AT&T. Those type of people are going to have a BGP network. Or maybe you're a large organization, you might have a small portion of BGP. But the main part right now, I want you to just know BGP is for ISP level only, and these other ones are what most organizations are going to run. So we're still using an IP level, an IP address scheme. So we're going to be using, IP4, 6. We can be using IPX and SPX and AppleTalk, but we're not probably going to be using those two anymore because we pretty much strictly talk IP now these days. So here we're learning the routing protocol is dynamically assigned. So when PC1 wants to get out to the internet, it's going to figure out its best method to get there. And here you can see one route may be better than the other route. So like an example, going to the top route may be faster, or maybe it'd be faster going this way. But you got to look at the cost of speed. So going through a 120K route would not be the quickest way going this way. Maybe going this way would be faster, or maybe this way would be going faster, because overall, if you're going to 56K, here you have 512, so this may be an overall better route. So these decisions are going to be made based on all the different metrics that the routing protocol is going to have. So we can use more than one routing protocol to make our decisions. Not a big problem. So we have our different metrics. So anything directly connected, we have what's called administrative distance cost. So anything directly connected is 0. If we static configure a network, it's a 1. If we're using EIGRP, that's 90. If we're using OSPF, that's 110. If we're using RIP, it's 120. And then if we're using external EIGRP, that's 170. And then, hey, we used to know what this route is and we don't know what it is anymore, it's 255. So here's a little note I want to factor out to you. So the EIGRP, that's a Cisco proprietary protocol. So same thing with the external. So if you're not running Cisco routers, you're not going to have that option. So you're going to have OSPF and RIP. And we're going to, as we go through all these different flavors of routing protocols, you got to remember some of these are older than others. And that's why they have different, they represent different ways of thinking and how to get there. So metrics can depend on, like an example, like RIP, EIGRP considers hop counts. How many networks do I need to go through? That's how they're going to make their decision. Like an example, bandwidth is going to be OSPF, EIGRP is going to use the bandwidth. So when we go back to like an example of that slide, here it's going to make a decision where, an example, RIP is going to go through hop count. So it's going to say right here, router 3, write down this link to router 2 and out the door to the internet. That's not necessarily the fastest way. Where the other ones are going to pick maybe this route here, because this is overall faster, or it may pick this way because it's more reliable, depending on the routing protocol you're going to use. It's going to make these choices. You can run all of them together. So this would be like an example. You're running OSPF and RIP, and you're pulling up your GPS and it says, hey, which one is the best way? Well, it's going to say, well, OSPF says is the better way, so that's going to be the preferred way, and then RIP will be the backup way. So if something happens and OSPF can't figure out how to get there, but RIP still can figure out how to get there, well, then that's going to be the decision making for that. So internal versus external gateway protocols, essentially, these internal gateway protocols, they're autonomous, so you're going to have an ID number. The external gateway protocols, they're going to connect you from an autonomous ID to a different ISP level. So this is where you have to be a very large organization, not maybe large in size, but maybe large in bandwidth, that you're going to have this, or preventing who your provider is can offer this. They may not be able to. So here they're showing an example of using BGP. You're going to get an autonomous ID number, which is an AS number, and you're going to use that to advertise your portion of the network. They're going to advertise their portion of the network. So you're going to use, like an example, you're going to use like RIP, OSPF, and all that in your internal network, and then you're going to use that ID to pass that on to the ISP. So if you had multiple routers on the internet that were publicly available, it would pass that data onto these, onto the ISP level, so then the traffic can flow to them. So routing advertised methods. Well, here's the two ways we can approach this. We can advertise, store the route information as follows. So example, distant vector will provide a full copy of the table sent to its neighbor regularly. So if you don't have a high bandwidth, this can slow your coverage time, because let's say every 30 seconds it updates the whole entire table across your WAN connection. If you don't have a very fast WAN connection, that can be a disadvantage. It may use a hop count as part of its metrics. You might have, void, loops are void by depending on timers and procedures, depending on the routing protocol. So one nice advantage with link state is it updates the table one time, and then after that, it only advertises what has changed. So if one route falls, it only passes that one piece of information out. So that's kind of nice, where a lot of the other ones didn't do that. So again, just like switches, we can have switching loops. We can the same thing have router loops. So we have two means of dealing with this. So we have split horizon, which is a feature to prevent routing being learned on one interface and being advertised by using the same interface. The other one is the poison reverse, where we poison reverse feature causing the route to receive on one interface to be advertised blocked out of that same interface with the same metrics to be considered to be infinity. And then EIGRP has its own method of dealing with this. So here's a little chart that breaks down how the routing protocols work. So again, RIP is distant vector. It uses hops. We have OSPF. So RIP and OSPF are both open standards out there. So RIP was first, OSPF came out later. So that used the link state. And then Cisco's proprietary enhanced internal gateway routing protocol uses advanced distant vector. It's also for internal use. And then we have the is-is, which is a link state internal routing protocol. And then we have the BGP, which is the border gateway protocol, which uses path vectors. It's external. Again, it's mainly what the ISP would use. So now the next thing we're getting into is NAT and PAT, which is our way of getting a private address and a public address. So like in Chapter 5, we learned what a private address and a public address is for. Our biggest problem is we said that a private address cannot be routed over the internet. A public address can be. So we use this feature called NAT. So we can do NAT and PAT. So PAT is a port translation, so we need one IP. We use the port numbers to distinguish a table, to distinguish where we're going. And NAT, we have to have multiple IPs. So we have to have multiple public IPs to do this. And then sometimes we do what's called an overload, where we use both of them, because maybe we got 5 IPs and you got 3,000 computers. Well, 5 IPs only means 5 people are going out. And then if we're using one IP, PAT, we have 65,000 port numbers. Well, think about it. How many computers, how many sessions do they have? One machine could have 20, 100 sessions, depending on how many tabs somebody has open, all the little programs running in the taskbar. All these things can make a difference. Oh, we may wind up using a combination of both. I'll show some examples.
Welcome back to Lee's Demos. I'm going to do an example of network translation. So here we have a network on our left using a private class C address. On the right, we're using a public address simulating the internet. So if we go into the router, let's just go to the CLI real quick. So if we do enable, show run, so you can see we have essentially a couple entries in our interface. So here you can see we have NAT inside for our private IP, NAT outside for our public IP. And then we're saying a NAT source using the interface. So we're saying use that IP address is our NATed address, creating an ACL to allow the traffic to go through. And that's pretty much it. So the next step, Hey.
Hello, how's it going?
All right.
Well, good. I was just reminding you about Bobby's new appointment.
Yeah, you said at noon, right?
Yes, I do. And then, just let her know that I probably am not going to be able to get him till 5 o'clock hour.
Okay.
So, I think she said that was okay, but I can't get there.
Okay.
And then, yeah, and then just, if you wouldn't mind asking her, like I told her to do the body or something, because it's so much longer, but just a little trim. I don't want him, like, shaved or anything.
Okay.
Okay?
All right.
No poodle cut. Make sure you just say no poodle cut.
Okay.
Thank you.
All right.
You want me to text you that, or you'll remember?
Yeah, you text me that. It's fine.
Okay.
All right.
Talk to you.
All right. Bye.
Bye.
All right. So we showed. Next, we're going to do show IP net translation. So you can see there's nothing to be found yet, so that's fine. So let's go ahead and open up our desktops. So right now, we're essentially not surfing the web or anything, so let's get these things going real quick. Typing. So there, you can see PC2 went across the switch through the router, through the net translations, through the switch, and then down to the server. So now let's go to this desktop. Type that in there. So, yes. So now if we go back to this router, show NAT. There we go. So now we can see we have our NAT table. So you can see here is the port number that is assigned to, showing that, PC1 is going here on port 80. And then you can see again, it has another IP address showing PC2 going here. So you can see the table. It's created as these connections. Once these connections drop, the table will eventually just, it'll be empty again. So that's just a quick demonstration to visualize how the NAT table works. Back to the slides. PAT just works the same way. We have a port as our placeholder. Multicast routing, the primary purpose of this is the Internet Group Management Protocol used by clients who want to join a multicast group, an independent multi-class where routes multicast between multicast enabled routes. That is a handful. So here they're showing an example of this where you can see the multicast receiver client has additional IPs. We're using a 239. Yes, we're using a Class D address to send this information out. So that is how we get into multicast type things. So we can use these for a number of different reasons. We would use multicast for, like example, imaging PCs. We'd make a master image. We go around, put a flash drive in each computer, boot it up, join this server. It's going to push out an image. So we can do it, everybody in the room. We can do it for partial of the people. So just to give some ideas on how we would use these things or why we use them. So the book goes into the two modes, the PIM, the defense mode, where we periodically flood and prune the behavior of this form to optimize distribution trees. This causes a negative performance impacts on the network, so rarely used. Then you have the PIM sphere model, which initiates use of shares of distribution trees, which may be subliminal, even creates a optimal distribution tree throughout the shortest path. So again, there's so much into knowing about routing protocols. Depending on your organization, you might not be involved in doing this. So here they're just showing an example of this where you're going through multiple networks. You can see discover a multicast receives clients proceeds defining the various paths required to send a multicast packet from a specific source to a client. In the defense mode, assumes that this is such the client would be in the same or close adjacent network. So again, doing the multicast, you may not be on the same subnet. Maybe, this would be like an example where I was going back talking about the imaging. That's not going to be on the same network. That's probably going to be on your server farm, and you're going to have multiple workstations, because these routers would not necessarily be the internet routers. These would be like your different layer 3 routers in your network that, like example, maybe having a voice network, a PC network, a printer network. You still need to route between them and have multiple switches and stuff like that. So just trying to give you some perspective on this. So again, here's an example. The book is talking about pruning. So it's just saying, hey, all right, we're not going to, we determined this is the best way of going here, down this way. So we're going to, prune away so that only the traffic flows this way. So then after pruning, we're just going through whatever routers we need to just get to that location. And then here the book is showing another example of the shared distribution tree, where it assists the traffic and parsing out mode that can be identified. The machine receives the multicast traffic on behalf of the client, and downstreams the receiver client do not know the true source of the address of the multicast, so they only need the IP. That's a handful. So here again, they're just using another technique to mitigate it propagating against all the routes, because it's a multicast environment or cast. Again, we could be sending out a video, we could be sending out a stream of imaging machines, different ways we can handle this. So the main thing you just need to understand, how do we mitigate these things? These are the two ways, using the PIM, the PIM, and the PIM-SM. These are the two different ways we can do that. So a quick summary. Basic routing. Source of routing information. Routing protocols. Administrative distance metrics. Internal, external routings. Vector versus link state. So again, routing protocols, we can make it static, we can make them dynamic, we can run the combination of both. A large organization, you're not going to want a static, because if something changes on your network, you're not going to get that dynamic update. So that's why a majority of everybody is going to use some type of routing protocol. And most organizations are going to be using OSPF or IGRP. If you're an all Cisco shop, you would use that, and if you're a blended, you would use OSPF. Would be your best choices. And then if you're an ISP or something much larger, you probably wind up using both. and using BGP. Alright, that concludes this chapter. Thanks for watching.